John is a software engineer with more than 15 years of experience in the field of IT. John has applied to the CTO position in a new startup. He passed the primary 2 interviews successfully, and he was selected among 5 applicants to go through the final interview. And after the evaluation of the final interview, John has been shown to be double qualified than each other applicant in this final round. Now, if I ask you, what are the chances that John got the job? Well, if I am the person to answer this question, I will give him a very high bet that he got the job because simply he was double qualified than any other applicant in the final interview. So I will bet for about 90% that John got the job. But do you know that according to Bayes' theory, and after the final evaluation of the interviews, John has almost 33% chance to get the job. Now you may ask yourself why our estimations seems to be very different from the estimations of Bayes' theorem. This is a very good question that I will answer later in this video. But first of all, let's understand Bayes' theory and how does it work. I think the best way to understand Bayes' theory is to think of it as a function of time. For instance, in our John case, if we reread the problem, we will see that we have 2 primary timestamps that can conclude the final evaluation of John and his chances to get the job. The first time frame, or let's call it T1, is the time frame before the final interview. The second time frame, or T2, is the time frame or timestamp after the final interview. And the way Bayes' theorem is work is to estimate the probability that John got the job in both timestamps or both time frames. The estimation we want to calculate here is usually called the hypothesis. So we can define our hypothesis H as the chances or the estimation that John got the job. At the first timestamp, all 5 applicants have equal opportunity to get the job. Then we can express the hypothesis or probability of H equal 1/5 or 20% chance, which is equally likely to go through any applicant, including John. The first estimation in Bayes' theorem is usually called the prior estimation, and we expressed it as probability of H. At the second timestamp, or at T2, we received a new information that John was double qualified than all other applicants. This new piece of information is usually called the evidence, or E. E is used to update our prior estimation, and the generated estimation after having the new information E is called the posterior estimation, and the posterior estimation is usually expressed by the conditional probability of E given of H given E, which means the probability of our hypothesis H given the new evidence E. Now the question would be, how can we update our prior hypothesis probability of H given the new evidence E? And here where Bayes' theorem came into the picture. Bayes' theorem bends the prior and the posterior by a component called the likelihood. The likelihood is nothing but the opposite conditional probability to the posterior, which means we express the likelihood as probability of evidence E given the hypothesis H. In words, we can express likelihood in our example as the probability that John was double qualified than all other applicants given that John got the job. To calculate the likelihood, we need to quantify our evidence E into ratios. For instance, let's say that the final interview has an evaluation sheet or evaluation test of 10 points. In this evaluation, John got, say, 8/10 points, while each other candidate got only 4 out of 10 points. Then we translate these ratios into probabilities as follows. We say that the probability that John is double qualified given that John got the job, or probability of the evidence E given the hypothesis H, equals 0.8, and the probability that John is double qualified given that John did not get the job. This is just the otherwise round of the first probability. We express it as the probability of E given none H. This little symbol means not, equals 0.4. This is just the complement of the likelihood. Now, as we calculate the prior and the likelihood, we are ready to write down the simple equation of Bayes' theorem as follows. We write it as the posterior is proportional to the likelihood times the prior. And note here that both sides are proportional to each other but not equal to each other. In order to equalize both sides of this relation, we need to normalize the right side by using another component called the marginal likelihood. Marginal likelihood is the total probability of seeing the evidence E whether the hypothesis H holds or not. We express it mathematically as follows. We say that the marginal likelihood equal the probability of E intersect H plus the probability of E intersect not H, which means that the likelihood is the summation of the probability that the evidence and the hypothesis occur plus the probability that the evidence and the complement of hypothesis occur. Note here that the first term in the marginal likelihood is expressed as the likelihood times the prior. The second term of the marginal likelihood is expressed by the complement of the likelihood times the complement of the prior. Now we have all the necessary components to write down the Bayes theorem and to calculate our estimation according to it. We say that the probability of our hypothesis H given the new evidence E equals the likelihood, the probability of E given H, times the prior probability, probability of H, divided by the likelihood times the probability in addition to the complement of the likelihood times the complement of the prior. And for simplicity and symmetry, the denominator of the right hand side is usually expressed as probability of E. And now we have the simple and most famous expression of Bayes' theorem. P of H given E equals to probability of E given H times probability of H divided by the marginal likelihood probability of E. Let's go back to our John case and plug in numbers and calculate the posterior according to Bayes' theorem. If we calculate it like this, here we have the likelihood that John got the job, the probability of the evidence given the hypothesis equals 0.8 times the prior probability, which is 0.2 or 20%, divided by the same value 0.8 times 0.2 plus the probability of E given not H, which is the probability that John did not get the job, equals 0.4, which is half the probability that John already got the job, times 0.8, which is the complement of the prior probability 0.2. If we calculate these values, we reach out the value of 1/3 or 33% that John has the chance to get the job, even if John is double qualified than all other 4 candidates in the final interview. Now I want to give you a visual representation of or visual interpretation of the Bayes theorem to give you more insight about how Bayes theorem works and how does it calculate this value. As I mentioned before, we have in our example 2 timestamps. The first timestamp is T1, which is before the final interview, and in this timestamp we draw our prior estimation or prior probability, and here we have each candidate, including John, has equal opportunity to get a job. So each candidate has an opportunity of 1/5 or 20% to get the job. At the second timestamp, or T2, which is after the final interview, here came the evidence that John was double qualified than any other candidate in the final interview, which gives John 2 parts as each other candidate in the final interview. This makes us, or make the Bayes theorem calculate the probability that John did not get the job with almost 4/6 or 67%, which is the summation of the probabilities of all other candidates other than John, and the probability that John got the job equals 2/6 or almost 33%, which is double the probability that any other candidate got the job. So this is a visual representation and interpretation of Bayes' theorem in our problem. Now I go back to the first question that I want to discuss in this video about the difference between our estimation and Bayes' theorem estimation to answer the question of John, whether he got the job or not. Now if we make a small comparison between our minds and Bayes' theorem and see why or from which root this difference came from. You may think that when Bayes' theorem estimate the chances of John that he got the job with 33%, that Bayes' theorem underestimated John's chances to get the job. But the fact is the other way around. The fact is that our brains have overestimated John's chances to get the job, not the other way around. And this is due a very common cognitive bias called availability heuristic. And in this bias, our minds unconsciously draw quick conclusions based on the first impressions we get. In John's case, the first impression is that John is the most qualified person to the job, and accordingly our minds have maximized his chances to get the job. This is why we draw a very high estimation that John got the job. We say that John is almost has already 90% chance to get the job. On the other hand, Bayes' rule quantifies each piece of information before drawing estimations. At the first timestamp at T1, Bayes' rule assigns equal chance of 20% to each of the 5 candidates in the final interview. After the final interview, Bayes' theorem has doubled John's chances to get the job without neglecting the fact that we have 4 other qualified candidates to have the job. So Bayes' theorem is just like our minds gave John the preference to get the job, but in more logical and quantitative way than our minds did. So it assigns 33% chance for John to get the job against only 16% chance for any other candidate to get the job. Now, as we have this simple example of how Bayes' theorem works and how it draws conclusions and estimations, we need to learn some important facts about Bayes' theorem. The first fact we have is that in Bayes' theorem, evidences update priors, not override or replace them. So the prior is the heart of any typical Bayesian estimation or Bayesian inference. Without having a clear definition of your prior, we are not, or you are not doing Bayesian inference, you are doing something else. So the prior estimation represents the primary estimation of our hypothesis before seeing any evidences. No matter how strong evidences are, they just update our prior estimation but not override or replace it. And this is very important to put it into your head before doing any Bayesian inference or any Bayesian estimation. In John's example, even if John was 3 times more qualified than any other candidates in the final interview, his chances to get the job will not exceed 43% according to Bayes' rule. If he is 4 times more qualified, his chances will not exceed 50%. So, as you noted here, that Bayes' rule increases John's chance according to his achievements in the interview. This is our evidence, without ignoring the fact that he is only one between 5 qualified candidates that went through the final interview and have the chance to get the job, which is the prior. So the evidences just update priors, not override or replace them. The second fact of Bayes' theorem, which may seems to contradict the first fact, but it doesn't, which is that strong evidences can drastically change Bayesian estimation. Let's have a simple update to John example to illustrate this fact. So let's say that after the final interview and before selecting the new CTO to the startup, the startup founders have received a feedback from a very important investor who was ready to finance their startup. This investor requested that the new CTO must be in office 5 days per week. When the founders went back to the 5 candidates, they found that for some social reasons, John was not able to be in office full time. He can only be in office 1 day per week, and the other 4 days per week he can work from home. But the other 4 candidates were ready to work 5 days per week in office. Now, if we have this new evidence or this new update, what are the chances that John got the job? In order to calculate the new posterior according to the new evidence, we need firstly to calculate the likelihood of the new evidence E2. So we write it like that. We say that the probability of that the CTO in office, which is the new evidence, given that John got the job, equal 1/5, because John is able to be in office only 1 day per week. While the probability that the CTO in office, given that John did not get the job, which means that the probability that the new CTO will work in office, given that the job went to another candidate, is equal to 1, because each other candidate in the final interview is ready to attend 5 days per week from office, or to work from office 5 days per week. So accordingly, we can calculate the marginal probability as follows: probability of E1 and E2, to evidence 1 and evidence 2, equal probability of evidence 1 and evidence 2 given the hypothesis times the probability of hypothesis, plus the probability of the complement of event 1 and event 2 times the probability of the complement of probability of our hypothesis. So we have the first component equals 0.8 times 0.2 times 0.2. Here we have the 0.8 that John was double qualified than any other candidate. So the value here is double the value here, times the probability that John, the new CTO in office, given that John got the job, which is 1/5 or 0.2, times the prior probability, or 0.2, plus 0.4 times 1, which is this value here, times 0.8, which is the complement of our prior hypothesis. If we calculate this value, we got the probability of marginal likelihood equals 0.352. And if we update our posterior accordingly, we will have the probability that John got the job given both evidences E1 and E2 equal 0.09. So as we see here, the new evidence E2 dropped John's chances to get the job from 33% after the first evidence to only 99% after the second evidence. And if we summarize John's chances to get the job according to Bayes' theorem, we can summarize it in this simple table. Here we have the three timestamps. The first timestamp where we draw our prior hypothesis, where before the final interview we give John 20% chance to get the job. The second timestamp was after the final interview, where we saw the first evidence that John double qualified any other candidate. Then this raises John's chances from 20% to 33% to get the job. And at the third timestamp, after the investor feedback, that we learned that John couldn't attend work full-time 5 days per week in office. This new evidence dropped John's chances from 33% to almost 9% to get the job. Here we learn that these strong evidences can drastically change the Bayesian estimation, and this what makes Bayes' theorem very, let's say, flexible tool and very realistic tool to estimate facts and to draw conclusions about our statistical problems according to each new update and each new evidence. Moving to the third fact in our video, it says that the likelihood is not a normal or not an event probability. This is also a very important fact that you need to learn about Bayes' theorem. Likelihood is a basic yet a very ambiguous component of Bayes' rule. But why is this? Many people treat likelihoods as probability values, and they get confused when they discover that it doesn't fulfill or meet probability postulations. Actually, the likelihood is a very special type of probability. It is not a normal probability, but it is a probability of hypothesis, or some references call it probability of probabilities. That means that the likelihood estimations are built upon human hypotheses, not upon event outcomes or test results. As a consequence, likelihoods do not meet the postulations of event probabilities. For instance, the likelihood and its complement must not sum up to 1. Also, likelihoods cannot be interpreted as informative ratios. So let's illustrate this example, this fact with John example. We saw in John example that the likelihood that John is double qualified given that John got the job equal 0.8. The complement of this likelihood, which is the probability that John is double qualified given that John did not get the job, equals 0.4, so half the value of the likelihood. As you note here that the summation of the likelihood probability plus the likelihood complement probability does not sum up to 1, and this is very common in likelihood because you are not here talking about event probabilities or normal probabilities, but what we call hypothesis probabilities. Also, please note that the likelihood and its complement can be expressed in different ways. We must not express them as 0.8 or 0.4. We can express it in any other way as long as the value of likelihood is double the value as the likelihood complement. So this is the very important concept of likelihood. No matter how you express them in numbers. So this is a very important concept of Bayes' theorem. The fourth fact about Bayes' theorem is that likelihoods are meaningless unless compared to each other, and this is actually the logical result of the third fact that we have already discussed now, that likelihoods cannot be interpreted as meaningful ratios or as meaningful percentages unless we compare them to each other. If you want to understand this fact, I would illustrate it with the following simple example. Let's suppose we have this golden ring, and we have 12 different jewelers, and we give the ring to each jeweler separately and ask him or her to estimate the ring weight according to his or her experience. And suppose we got this values or these estimations of the ring weight from the 12 jewelers. Of course, as expected, that the 12 weights are different from each other because each jeweler has estimated the weight of the ring according to his or her experience and hand sensitivity and so on. So we have different estimations or different values of the ring weight. Now, if we want to make a general estimation or make a general conclusion of the ring weight according to these 12 feedbacks or these 12 estimations from the 12 jewelers we have. In fact, we cannot prefer one value over another because at the end of the day we know that all of these estimations are just human estimations and cannot be qualified as measurement as true measurement using certain device, for instance. So the way we can predict the most common value to be correct in this problem is to count how many times each weight was repeated from the estimations of these jewelers, and the value or the weight with maximum number of repetitions would be the value which would be the most trusted value or the most reliable value of estimating the ring weight. So we can count the likelihood of each estimation that came from jewelers. We can see here that we have 5 different values of ring weights, and each value has certain repetitions. This value is repeated 1 time, this is repeated 3 times, 3.9 has been received 5 times, and so on. And also we can visually express these different likelihoods in this nice histogram where we express the probability of each value according to its repetitions or each occurrences in the estimations we have received from jewelers. And we found that the weight 3.9, which is just here, gains the maximum likelihood with 5/12 or a probability of 0.42. And this is a very common technique in statistics called the maximum likelihood estimation, where we draw the estimations or quantify the estimations we received and assign the value that is much repeated in our likelihoods to be the more reliable or the more common value or the more close value to the true value. In addition to learning the maximum likelihood or the maximum value of these human estimations, we can also define range of reliability. And the range of reliability covers certain range of our data that covers the highest percentage of readings. For instance, in our example, we have here this range of reliability. The range between 3.87 and 3.93 covers almost 90% of the values of the that we have received, or the estimations we have received from our jewelers. And this interval or this range is usually called the credible interval or the highest posterior density. And of course, we can shrink or expand this credible interval to cover less or more percentage of the data at hand, to have more convenient conclusions and more understanding of the likelihoods we obtained from jewelers or from our data. The fifth and last fact in this video about Bayes' theorem is that marginal likelihood is constant over all hypotheses. Let's recall Bayes' rule and see how we define it. We have the posterior on the left hand side equals the likelihood times prior divided by the marginal likelihood. Technically speaking, the single rule of marginal likelihood is to normalize the posterior probability to be a valid ratio, which means to be between 0 and 1, because other way around, and according to the nature of the likelihood probability, if we do not include the marginal likelihood in this equation, we could have posterior values over than 1. This is a very critical rule of marginal likelihood. However, if we had a look over the posterior definition of multiple hypotheses, we will notice that the marginal likelihood does not change over different hypotheses, because it is independent from the value of hypothesis. It is an integration of all hypotheses of our problems. Here, if we estimate the posterior of h given E, we will have the definition of marginal likelihood equals the probability of E given h times probability of h plus probability of E given not h times probability of not h. If we want to calculate the complement of this hypothesis or the complement of this posterior, we notice that the change will happen in the numerator, but the denominator or the marginal likelihood it gives the same value. And this is a very important fact of Bayes' theorem that is very helpful in certain applications of Bayesian inference. For instance, if you calculate the maximum likelihood estimation, you don't need to calculate the marginal likelihood, because you just ignore the prior probability, and accordingly you don't need to estimate or to plug the marginal likelihood in your equation. Also, in other algorithms that are inherited from Bayesian rule, like for instance the naive Bayes classifier, if you calculate the naive Bayes classifier for multiple values, then all what you need is to compare the posterior values of multiple classes, and in this case also you do not need to include or to calculate the marginal likelihood of your problem. So this is a very helpful fact to learn about the marginal likelihood. The last part of this video is about the proof of Bayes' theorem, which is very simple, as I think. You know that easily Bayes' theorem can be easily inferred from the joint probability axiom of two independent events A and B. We learned from the the theory of probabilities, that the probability of A intersect B equals the probability of A given B times the probability of B. And accordingly, we can in the same way write it the other way around. We can say that the probability of B intersect A, which is this part, equals the probability of B given A times the probability of A. And as joint probabilities are interchangeable, which means that the probability of A intersect B is the same as the probability of B intersect A, that makes the right hand side parts are also equal to each other. So we can write easily that the probability of A given B times probability of B equals the probability of B given A times probability of A, which is easily give us the Bayes rule. The probability of A given B equals the probability of B given A times probability of A divided by probability of B. So thank you so much for your time watching this video. If you have any questions, leave them in the comments below, and I will make my best to answer them. And yes, till the next video, thank you and have a nice day.